let's assume that for some problem this is some linear regression. So in this we can find that in our x-axis it's the size of the house is one parameter, and our y-axis is price of the house, and here we can find among the plot we can find three lines. So these are three trends. One is red in color, and another is green in color, and another one is purple in color. And how can I confirm that this is better, this is better? If I draw, I can fit the lines to some extent. If someone draws and someone, they can fit to some extent, but we can't we can't make a conclusion that this is the best line. We should have some system. Then how to find that? So for those questions we have answers that lies with cost function. Okay, even if the cost function is defined, cost function is nothing but it's a error. In this model I have used theta1 is the only one parameter. Accordingly I got the values. The error is nothing but the deviation between the predicted one versus actual one. So this is the ground truth and this is the predicted term. So I'm finding the difference and then considering them, then stating it as total error. Okay, if I do like that, then what happens is so this is the green line as now I'm considering the green line as my prediction, and this blue color dots, these are all the actual points. These red color things, hinges we can find. These are all the actual error terms that we are seeing. The total error here represents total error here represents magnitude of this amplitude of the signals. So from here to, in some cases it will be positive, in some cases it will be negative. What happens is here it is above this line, so the distance above, and in this here the difference is negative because it is below the line. So some cancelled, some amplitudes are getting cancelled among each other. So to avoid that, so that problem happens. Some is negative and some numbers are positive. In order to avoid that, we will be using squared error. That is called mean square. We will average them, so it is called mean squared error. And this mean square, this is the cost function. If someone says, yeah, this is the best fit line, then what we have to do is we will do the mean square error. Then if the mean square error is comparatively less than what is existing, then we can say it is a better one. Yeah, this is how this mean square error is also it is termed as cost function. Okay, so let's skip this. Yeah, I hope it will be clear till this point. Let's try this once. This is called guess the number. In this, the system will assume some number that as a human, when we interpret, we have to find it out what the number is. So now within the range of 20, system will assume some number within 20. Now I'm able to find what the number is. So at first I'm guessing it as some 15. Then system is telling me my guess is too high. I have to give a number something lesser than 15. So I'm reducing it to 10. Then again system is asking me to come down, asking me to come some lesser number. So I am changing it to 5. It is still asking me to go to a number something lesser than 5. So I am taking to 3. Still it is telling me, so I am going to 2. So yeah, in this case, so 1 is the solution. Yeah, what we have seen here is we will be doing something. Let's call it as finding the gradient. When we find the gradient, we can get the information of whether we have to increase or decrease some direction. We will get, but we don't get any magnitude. Then after getting the direction, the numbers, I'm changing number 15 to 10, 5. It's everything, it's up to me. The choice is mine. uh, why I am doing is because just my intuition, no other reasons. The guesses initially I made is 15, then 10. These are the guesses that I made, and the steps we can find it. I subtracted 5 from 15, then I got 10. Then again I subtracted 5, then I got 5. So these are all the steps that I have taken, and the step is not uniform. Okay, so now let's jump to gradient descent. So this is how, in the same way, uh, we we will be having function. In that function, the parameters theta will be initialized randomly. Initialize something randomly, and we will take some step. Within that step, we will find the gradient, and we will ask. We will, using gradient, we can decide we have to decrease or increase. We will get some solution, some direction. Then we have to take some step. Then we will reiterate it until no more. Even if we increase, then there is no effect. When there is a negligible effect in making, till that point of time we will make it. This is what gradient descent is. Okay. What happens actually, behind what happens is, so I want this purple line. This is the one line. After gradient descent, something has been learned, so it will be moving upward. Then after some period of time, it will be moving upward. So actually what happens is, it's the slope will be computed. Yeah. Here in this diagram we can find that, don't worry about the mathematics stuffs. If it doesn't, if it understands, that's fine. If it doesn't, that's also fine. If we read it a few times, then we will get it. That's fine. That is absolutely normal. So please don't worry about that. What this is some function. So in this, the first order derivative, what we can find it, when it is green color, it is increasing, it is moving up. When it is red color, it is moving down. That we can observe it from the figure. The same thing is happening with our theta. Our goal is to minimize the theta so that it represents, our goal is to minimize our cost function so that it represents, sorry for a wrong notation in the symbols that I have mentioned here, that we have to represent. So that's the reason we have to approximate the labels y with theta and x, and this theta, the values of the theta are fully randomly initialized. Yeah. Okay. So what the gradient descent is: find the gradient, calculate the step as per the learning rate, then update the parameters, then check for convergence. So these steps has to be repeated forever. Okay. Then how to find the gradient? Okay, let's jump. Let's see an example with only for a well-defined function. Well-defined function means the variables, everything is defined properly. So as seen, sometimes before we might have seen this. So find the minimum of a function. So here the parameters, what is the parameters is x is the only one parameter. It is quadrupled and cubed here. The same is uh, coded here. This is lambda function. Here x power 4 minus 3x cube plus 2. It has been written here, and we will plot it as a brute force approach. When we plot in this range, this is the exact plot of the numbers that we are seeing here. The diagram corresponds to the function x power 4 minus 3x cube plus 2. And here we can find that at 2.5 the value is minimum. Okay, now let's use derivative is also known as gradient are also known as slope. I'm sorry they are interchangingly used. Since it is only one variable, we can say that here gradient is same as derivative, but it is not the case always. Give me some time, I will clarify you. Don't worry about everything whatever written here. Please ignore this, and we will what we will do is we will apply gradient descent. Before applying gradient descent, let's check the derivative of that. I know that the first order derivative for that function is x square into 4x minus 9. Yeah, x square into 4x minus 9. So that's what is reflected here. And if we plot the same, what we can find is the derivative value is 0 at the point when x is 0, the derivative is 0. When x is 2.25, the derivative is 0. So team, am I in the right direction? Are we able to follow any questions so far? Hello?
I'm following. I'm finding it helpful as well.
Yeah. So are you able to follow? I'm just asking. I mean too fast.
I think it's fine for me.
Okay. Yeah. Thanks. Okay. Then this is the diagram. In this we have plotted the original function and the derivative. The blue color is the gradient, and the green color is the actual function. So when the gradient is 0, we can. That's the point when there is no slope. We can, when there is no slope, in the sense the slope is 0, or else what we can see, the instantaneous rate of change at that point is negligible, very negligible. Okay, when then the same we can solve using gradient descent. So to solve using gradient descent, what we need is we are optimizing the parameters in ML problem. We are optimizing the parameters for theta. In this section, in this problem, the problem that we have seen just above, here we will optimize the value of x. So what are the steps? Find the gradient, find the step, update the parameters, then check for convergence. Okay, so we will randomly initialize with some starting value. Then what the learning rate will be 0.01 here. This is step size. Then we should know the derivative. For this function, I know this is the derivative. 4x cube minus 9 into x square. I have written here. Then what just for one iteration I am manually doing, finding the gradient, find the steps, then update the parameter, then check for convergence. So I'm finding the gradient here. What the gradient will give me? It will give me the direction, on which direction it has to go. It will give me some number. Okay, so the gradient will give me, so here we are seeing, right, 180 minus 189. So it will give me some number, and accordingly then I will find the step. The step size is in our ML term we will say this as our learning rate. Then with this learning rate, I'm making some step. I know the direction, and what step I have to take, that I have to decide based on my learning rate. Once I decided, then I will update the parameters. Then I will check for whether the difference is there will be some stage this x will be saturated, it does not grow beyond. So we have to do this process till that step. Okay, then again I am doing the same step, updating the gradient, finding the step size. uh, so now we can find that the gradient has significantly reduced. Now in this point, the function, this is the original function, we have reached it till minus 6.5. So this is not the actual minimum. The actual minimum lies around 20 point something around 2.25 something I guess. Okay. Mm. So we will do it in iterative in a program. So till some n number of iterations, we are finding the gradient, find the step, update the parameters. Likewise, if you do, you can see that this gradient has started with this one, 1188, then it has reduced to increased to minus 4.94, and then minus 6.631. So it is jumping somewhere, and then over the period of time it has grown to 0.349. Then at some period it does not converge, so no more iteration, so it halted at the 62nd iteration.
Rajesh, I just had one quick question.
Yes please, yes please.
So when you update the x value, right, you're subtracting the step from it. So x equals x minus step, right?
Mm.
Is that the way of ensuring? So that's how we know that we will always be moving in the direction that reduces it, right? So it'll never, the gradient will never go.
I'm sorry, can you please bit louder?
Yeah, I was just saying, if we, because we have x equals x minus step, does that mean that's how we ensure that we're always going downhill in the plot?
Yeah, very good question, very good. Yeah, thanks for this question. The thing is, here the diagram in the left side. Okay, why this is bowl shape, that is different question. Let's ignore about that, but just stick to that. This is somehow this is our cost function looks like. If we initialize our parameter theta, then we may be lying somewhere in the mouse pointer that we are seeing here. We will be something like lying here at first. Then our ultimate goal is we have to reach the minimum. So we have to take downwards. Even if we start from here in this side, we have to take downwards. So even if we start from here, we have to take downwards. Since the function that we are working on, we know pretty very well that the function is it's called convex function. They will say it's a convex function, and uh, and we are finding minimum, so we are negating it with the step size. And the question that you have asked, exactly, here we are getting some negative values. Am I right? Hello?
Yeah.
Yeah, in the steps we can find that the value is very negative, but here this again this negation will give me some positive. So that's what you are thinking, am I right?
That's
Yeah,
right.
so the idea is that the gradient tells you the direction in which the function is increasing, but you want to go to the direction that the function is decreasing, and that's why you subtract the gradient
Mm.
instead of adding it.
Yeah, that why the decrease is because I have initiated my x with minus 6. I have initiated x with minus 6. Let's come here. I have initiated x with minus 6. At first, when x is equal to minus 6, the corresponding y value is 1946. Then after my first round of gradient iteration, my x value is decreased like this. And this is my y value. Since this is minus 6, adding some step size, it will increase its value. For this function, the function that we are seeing, in this case, the step size, this value is like this. So once minus 6, then 5, then over the period of time, it has grown till 2.25. So the same thing, if you plot, we will be starting minus 6 at first, and then it starts with here. Then the first iteration, suddenly it will jump here. Then the second iteration, it will jump here. Then over, then the learning keeps on something here, lies here. If you want to zoom in, it will be like this. It will reach here, then it will move in this direction. The gradient will move. Still, if you want, if we zoom in further, we can find like this. It will traverse along. In this data, in this function, there is no much noise. In our real time, we can find a lot of noise. Yeah. What's the point here is, we should, if it is gradient descent, we should remember 4 steps. The four steps are: find the gradient, compute the step, find the gradient, compute the step, update the parameters, then check for convergence. So these are the 4 mandatory steps in gradient descent. And okay, so in our case, let's come to our exact our problem. We are seeing some linear regression, and we are having the cost function like this. So why this cost function is like this U-shaped? Why? Because what is the cost function that we are using is this. Yeah, the cost function that we are using is error square. We are trying to minimize this, and if we find the diagram for here you can see that ax square plus bx plus c. So whatever, when there is a quadratic term, the degree that we can find here in this equation, x is the unknown, so x square is there. In our case, the error function, just assume that the error is the only one parameter. Instead of considering this, just for understanding, and I'm just telling, just consider error as the only one term. If we consider like that, then whatever be the function, it will be something like this. The shape is, it has been well identified very well. So that's why we are seeing like this in real time. Since for our visualization, we are seeing with only one dimensional. If there are multi-dimensional, you can think of it like some so it will be like something like this. Sometimes inverse also. For our case, we never get this. This legs down, we don't get that. And okay, so let's leave this. Yeah, we will see something like this, bowl shaped like this. And if you see in 3D, then we can find it like that. Yeah, this is how real time the parameters will move along. For our imagination only, this is part. The thing is, it will, if you consider only one parameter at a time, it will be like some U-shaped curve, some elongated U or pro-elongated U, something like that. It will be like this. Okay, so Let me be back here. Okay. So why it is U shape, something shape in the form of U shape? Because we are using errors. We are trying to minimize the error, and the order that we have taken is square form. That's why it is in the U shape format. Okay. Mm, okay. So depends on our learning rate, the step that I have taken, that varies with respect to the learning rate. If I am jumping from here to here with some learning rate, if my learning rate is very high, I will jump from here to here, then here to here, I may overshoot this minimum. So that chances may occur. So that's what is happening here. So what happens when the learning rate is very high? So it will start from something, then it will be jumping hither and thither, never reach minimum. In some cases, when when there are some noises involved, there is something called local minimum and global minimum, and the plateau. Plateau is somewhat there will be no there will be no very much difference in the slope. The global minimum is the most optimal point, and the local minimum is better, but not better than the global minimum. So if we randomly initialize on this side, somewhere this, on the left part of this curve, we may end up with learning rate here. We may end up with falling in the local minimum, unless if our learning rate is very high, then there is a chance that we may jump out of here, and then we may or may not reach. So that is beyond. It's just trial and error, and we can't guarantee it, but we can guarantee that gradient descent will take you to the uh, local minimum at any point. Yeah. The next thing that we can see is, yeah, we have seen this, right? So the gradient descent looks like something bowl, like some U kind of stuff. To visualize it better, what if your drone camera is sent above our top of the building? So how it looks like? It will be look like some squares, some rectangles, right? Our as if we are seeing from maps. In the same way, since the function that we have seen is our function cost function that we are seeing is mean square error. If we see it from the top, it will be like some circular form. This will be little bit hard to digest, but that's the fact that that's the reason this is called contour plots. The diagram that we are seeing in the left, this is called contour plots. Why it is circular in nature? Because the function that we have chosen is minimization. That's a squared form. Equation of circle is one thing that is parameterized with radius. That form is somewhat similar, so the contour looks like that, looks like circular in form here. That's the reason it is taking circular form, because we can't make this when the dimensions are very, just for the understanding we can see it now, but in our practical purpose we will mostly we can see this contour plots. Okay. This is the diagram on the left we are seeing. This corresponds when our input features are very are highly normalized everything. Then when we normalized everything, we will have all the variables. It will be scaled after normalization. It will be normalized such that the mean will be subtracted, and then the standard deviation will be divided. So it will be in the range of Gaussian distribution 0, 1. Gaussian distribution with mean 0 and standard deviation 1. So it facilitates computation quickly. Facilitates computation. If we don't do that, we will be seeing something in circular form, but some pro-elongated kind of circular form. then it reaches some hither and thither, it will move there, and then it will reach the minimum point. Okay, then now let's come to another thing. We are in gradient descent. I told you 4 steps. First one is compute the gradient. Second one is calculate the step. Third one is update parameters. And fourth one is check for convergence. How often we are computing the how often we are updating the parameters, that matters. Accordingly, we can see that batch gradient descent, and another one is stochastic gradient descent, and the next one is mini batch gradient descent. Okay, in stochastic gradient descent, what we are doing is, for every input example, we will compute the gradient, we will update the parameters. Okay, in mini batch gradient descent, we will accumulate examples, some examples, till some count. For example, we will take some 10 examples, 10 inputs, then we will compute the gradients, then we will update the parameters. Then again, for the next 10 different inputs, we will compute the gradients, we will update the parameters. So that process will happen. Similarly, in batch gradient descent, we will compute gradient for all at a time. For all input examples at a
Hey,
time.
Rajesh, if I can, before we talk about the different types of gradient descent, the point that he mentions about feature scaling of the different feature is a very good point to to pause there, because this is very often used, because, for example, if you don't do the feature scaling, you will see that it will be very slow, but actually doing the feature scaling actually helps. So always we want to feature scale. So, and if you want to talk maybe a bit about that, yeah, feel free. And that's what he has there, like on the warning, right? Yep.
Yeah, yes, Salim. Yeah, thanks for adding. The thing is, yeah, as Salim said, the importance of feature scaling, the author has told us, if we want to converge too quickly, then we have to do feature scaling. Even if it don't do also, it will do, but it is computationally a bit heavy. Am I right, Salim?
Yeah. It's just yeah. So it is just slower when you don't do the feature scaling.
Okay.
I mean, it's more than that. If you wanna talk more about it. So but why is it slower? It's just really if it's just going back to the math. So if we just, for example, think if we have like just different ranges, and if we're gonna like do the derivatives on just different ranges, it will be slower than if we scale all the features, say for example, to be between -1 and 1, and then we calculate the partial derivatives and all that. That's the main reason. It's just
Okay. Yeah. So so far we have seen only derivative. There is something called partial derivative and gradient. So these 3 terms are somewhat interrelated. And yeah, so this is our function h, and this is our h of x, and this is our, for our cost function. Usually we will divide 1 by 2 divided by the, here the m corresponds to the number of examples, number of the inputs that we have. We can say it as minimizing the function 2x is same as the minimizing the function 4x. So whatever the constant comes along with the function, that does not deal that doesn't play much role while doing the optimization. So just to ignore that, here in our scenario we have seen 1 by m. 1 by 2 m. M is the number of input samples. Then this is what we are doing. So update the parameters with the learning rate into the gradient that we are finding. If we say derivative, when we have only one variable, only x1 alone is there in our we are considering. At that time, telling that taking derivative, that is fine. But when we have multiple variables, we will be taking partial derivative. Then the vector of those partial derivative is called gradient. There are much more depth inside. I'm not that much. I don't have that much knowledge. This is the this. So far, I have understood like this. This, yeah. So the gradient is some vector of partial derivatives, and the vector of partial derivatives corresponds to in our case, if we have some 5 theta values, then we have the 5 partial derivatives. Okay. So here we can find that we are optimizing towards theta. In our math, if x square is something, then we have to make a derivative. Then we will change that as 2x with some mathematics, and then there is some inner function inside. So that's why they put the 2 at the front, and then they are separating this h theta of x separately. Okay, so to do that, again they are handling it separately, and after that, here the theta is the only one parameter here. For example, if x is 5x is, if you derivate 5x with respect to x, then we will get 5. In the same way, they did here. So since we are taking derivative with respect to x, with respect to theta, then we are getting x here. So now we know this is the gradient. Now I just plug in into this equation here. After plugging in, what I get is, this is my value, theta equal to plus alpha into this is called least mean squares update rule. Yeah. So this thing has to be done till some convergence. The same thing is author mentioned here, but in I told you, right? So adding the example of m, we are minimizing 2x and we are minimizing 4x. Both are same. So whatever the constant that comes in front, that doesn't make while doing optimization, that doesn't make sense. So that's why we can compare like that. Yeah. So we will be having partial derivatives, the vector of partial derivatives for each theta. That is called gradient. Now this now you can see that gradient is a vector, and gradient vector composes of partial derivative for the each parameter theta. Then if we make everything in one single shot, then we can code like this: 2 by m, the x corresponds to our matrix, and this theta is the number of parameters that we have. So this is the gradient for this. So the gradient computation he has simplified, and this same is coded here. Okay, this is not required. Okay, here we will see. Okay, then here for gradient descent means, please remember the four points. First one is compute the gradient, second one is calculate the step, then the third one is update the parameters, then the fourth one is optionally check for convergence. In the functions, if the functions are very well defined, the example that we have seen as here. So this is something well defined function. If something is defined like that, what we can do is checking for convergence is matters, because there will be only one global minimum. So we can see it here also. in our programming, in our problem-based scenario, we can find this n number of depends on the data. We can find something like this when we apply cost function over different values. So some local minimum will be there, some global minimum will be there. So it will be noisy. So in these times, we can't check for convergence. We can check if we get, it's our luck. It's based on trial and error. So that's why they are doing for some n number of iterations. They are doing the same. So they are computing the gradients. After computing the gradient, we have to calculate the step. That step part is being done here. Then we have to update the parameters. So that is being the third step done here. Then the fourth step, optionally, just keep putting the check for convergence. Okay. Then what happens when the learning rate is 0.02? The model starts from the red line in the ground below. When the learning rate is 0.02, it will learn from here till here, because we made something called iterations, right? Here we specified some 1000 iterations. So 1000 times it has learned like this. If you put n equal to 0.01, so the learning is varies till like it. If you put n equal to neta equal to 0.5, it is going like this, going upwards. So this is with respect to the learning rates, how the gradient descent is impacting. This is with respect to now we are seeing the learning rate with respect to our data x1. Here we have seen the same learning rate with respect to the cost function. So if we start from here, if the learning rate is very high, we will be moving hither and thither, but we will not be reaching the global minimum. If it is too small, we will be taking very smaller steps in the theta space. In the space of theta, we will be seeing like that. If we the thing is theta, if we change something theta, what's our goal? Our goal is to minimize the cost function theta such that the y is approximated with the this theta dot x that inputs. That's why if we change theta, then this value of the y, the quality of the y will get improved. Accordingly, the error function will improve. Yeah, that's the reason. Then yeah, the stochastic gradient descent and batch gradient descent and mini batch gradient descent. Only one thing: how often we compute the gradient, that determines what these three are. For every example, I'm computing.
If I can just there
Yes,
are
sir.
also 2 points to mention. Maybe and he did mention them very so you see how he is comparing actually gradient descent. I mean, gradient descent is just one way of optimization. There are other ways of optimization, like the normal equation or the singular value decomposition. So it is important to know, for example, why are we really using gradient descent, for instance, instead of the normal equation? I mean, the normal equation would still work, and I believe here that's why he said, let's if you can go up, please. Yeah. No. When you had the graphs, where you had the three plots next to each other.
You mean this?
The three plots that you were just showing with the different learning rates. Yeah, so exactly. I mean, this one. Okay, so that's the normal equation. So this one would also exactly. So this one also still works for finding whatever we're looking at. So for example, here we're looking to minimize the cost function. So this optimization method also works, and the gradient descent also work, but we favor the gradient descent because again, this one is very computationally expensive, especially imagine if you have a very large data set. Look at that. I mean to actually multiply two matrices, that's very, very computational. So, and that's primarily the main reason why gradient descent is very favorable with larger data sets. So just to be clear on that. So it's not the only one, and same thing with SVD, and yeah, I just wanted to make that point for if anybody is wondering, you know, is that the only optimization? It's not. So and that's why he says, like, under those plots, he says, I think, hey, you know, we get both the same. If you just go under the three plots, he says, oh yeah, we get the same result between from the two, right? Yeah. I just wanted to
I would just interject that in some of the papers that I've read going back to the 2000s, there was a number of people that are doing work on particle swarm optimization, and also something called, I think, BPO. It was another particle method, and I forget the exact name, but these were considered viable alternatives to gradient descent, but gradient descent just won out eventually.
Sorry, please come again.
That's good. I just wanted to make that point. Just, you know, since we started talking about the gradient descent, that it's just one optimization method. Like I think Stephen, he mentioned, yes, there may be others. I mean, the most popular ones is the normal equation, is SVD with gradient descent. I'm sure maybe there are so many others, but yeah, here it's mainly used because of it is favorable with large data sets for the computation. I just wanted to make that. And then he also, I think he talks about like when you were just showing the three plots, I believe they had different learning rates, I think, right? If you go up just to those. And I think we talked about that before. So we talked about how do we go about finding the best learning rate, right? Yeah, exactly. So you see how there he used the 0.02, 0.1, and 0.5. And I think before, I remember that we talked about how do we go about finding the learning rate, and I think he has there like grid search is one of them, and usually if he usually it's also good to note that when we change, let's say, for example, okay, you're using grid search and you're picking your best learning rate. Usually you don't change it. For example, let's say the first one, 0.02, you're not gonna go really usually 0.03, but what you do, you change it on the log scale. And that's so, for example, you would either change it, for example, either much smaller, like 0.0002, or like you would just do like 0.02, for instance. So that's also very common. Yep. That's all from my side I wanted to add. Thanks, Rajesh.
Yeah.
That's a really good point, Salim, that we, even though we have an analytic method to get the answer, which is the normal equations, we don't use it because stochastic gradient descent in general is better because it handles large problems, and the normal equations break down when you try to apply them to large problems. There's just too much compute overhead. But the other thing is that the normal equations are only good for linear problems, and in machine learning we rarely have just a linear, well, we sometimes have linear problems, but we also want to be able to handle nonlinear problems that are not representable as linear problems. In this chapter we saw how some nonlinear problems can be represented as linear problems. If it's a sum of, if it's a polynomial, then you can recast it as a sum of linear terms. And you can even do that when you have an additive function that has even a mixture of polynomial terms and sinusoidal terms. You can still make that into a linear model. But there are a lot of cases where you cannot cast it in terms of a linear model. And in that case, stochastic gradient descent always gives you an answer, and you don't have to worry about having, it's a general method. It doesn't care whether the equations are linear or nonlinear.
Yeah. Yeah. Thanks, Joseph, and thanks for adding. As they said, these things, the normal equations is mainly for linear problems, and the thing that we are seeing gradient descent, it handles linear as well as non-linear. The thing that main thing about the gradient descent is it will find, depends on the starting point where we are, it will optimize still the local minimum, and based on the steps that we are taking, it may overshoot or not. So that we have to how we have to define our convergence in the gradient descent practice. To check those kind of stuffs, we will see this one. This is in stochastic gradient descent. We will update the parameters for each and every input that we will get. So here, for the first input that we get, we will start with here. Then for the second input, in the contour plot, this is visualizing the parameters theta naught and then theta 1, as if we are seeing from the drone camera from the top view. If we see from left side or right side of that, it will be like some bowl shaped. In contour plot, it will be like we will be seeing it from the top view, so that we can visualize betterly. We can't see the depth, but we can see that how much steps it has taken, in the sense how it is moving left and right, but we can't see how it is moving up and down. Yeah. So it will be starting for each and every instance, it will be getting changed. The parameters will be getting changed, so accordingly we will get the optimal point. So the input that we receive is very random. Because of that, there is the path it has taken is also very random in stochastic gradient descent. Okay. In mini batch gradient descent, we will be taking some n number of examples, and then we will be doing the gradient updates. That's what the red color line that we are seeing, that is for stochastic. The green color line that we are seeing, that is for mini batch gradient descent. We will accumulate some number of points. What it is, the parameter theta will get updated for some 10 examples, or just for a sake I'm telling, for some 10 or some 10 examples or some 12 examples, something like that. Then again the next 12 examples will some. So instead of doing 12 times as in stochastic, we will be learning everything that corresponds to the 12 examples at a time. So somewhat lesser deviations in the mini batch gradient descent. When we check with the batch gradient descent, we are taking the entire data set, and then we are doing the computation, and then we are iteratingly towards. That's why it is much smoother compared to that. And some comparison among the hyperparameters, scaling required, linear regression, and the stochastic gradient descent. For this, when the number of m is the number of examples and n is the number of theta parameters. So the theta vector is, if it is increasing, what happens? So like that, some exhaustive study he has done that, and he has put us then. Okay, yeah. In stochastic gradient descent, we will be moving hither and thither to make that there is something, the learning schedule. He has implemented that one called learning schedule. Instead of having the standard learning rate, we can change the learning rate at some point when the steps, when there is no much difference Here depends on the iteration. He is changing that. In some cases, if there is no convergence, very less convergence, then take small. At first, we will start with some bigger steps. That's clear. Okay. At first, we will start with some bigger step, then bigger step. Then from here, if we find the gradient, it will be somewhat lesser compared to the previous one. So we will reduce our learning rate. Then we will take smaller steps. Take bigger steps at start. Once you are based on the convergence, you can change the steps. So the point. So these are so far. This is gradient descent. Everything is up to us. And yeah, is there any other questions in gradient descent stuff?
The gradient descent really can actually be a big discussion, because like here we'll get to talk, you know, like how we saw the local minimum and all that. So maybe it would be handy to kind of maybe talk a little bit about local minimums sometimes are not necessarily the global minimums and so forth. And yeah.
That Rajesh Kumar, you had a really great simulation playing on the right-hand screen where you had that sheet where the the ball was rolling down the sheet and finding the local minimum sometimes and the global minimum other times. That's a really great simulation that you put in.
Yeah, I mean,
Yep, exactly. Yeah.
Wikipedia has to be created. I'm sorry.
So the question then that would follow that, when do we really know that are we at the global? Yeah, so exactly. So you can see that for example, let's say for example now if we're using like a very small learning rate, it will just stay there. It will actually just get that right there, the one that we just passed, and it will never actually even move to try to find the global minimum, the global minimum, right? And that's why sometimes when we get to that first local minimum, the right thing to do is we want to like be able to maybe kick it out of that, so we may be able to find really the global minimum. But that's just
yeah, Salim, if you want to annotate, please have annotation.
I think that's good. I think
you can also see right now it's near a saddle point, and if the learning rate is small, then you might end up getting stuck at the saddle point, because then the slope becomes 0 at the saddle point, and so it will eventually, if the learning rate is small, then the step size will be less than the tolerance, and then it will decide to stop there. So another thing, you can get stuck at a saddle point. And then someone in the chat was talking about that there's one way to make sure you don't get stuck in a saddle point, and that's to calculate the second derivative and make sure that the second derivative, I guess there's a condition to figure out whether you're at a saddle point or not, and you could use that to stop it if it tries to, I mean, to make it keep going if it's reached a saddle point.
Yeah, and to follow up, Joseph, this saddle point is a very is a key on and by the way, guys, if I don't think maybe even the word saddle point was mentioned in this chapter, but there's something, but there's something to be aware, you know, to be aware of. What's a saddle point? Usually a saddle point we don't really see it now here, because this is like really more. It's like just 2D, but if you want to see something like 3D, or maybe if Rajesh, maybe if you just want to Google saddle point so everyone can see that, you yeah. So but yeah, that's a key there. That's exactly. So yeah, just any of the images that were at the top. Yeah, see, you see, so that's it does look like a horse saddle, right? So yeah, so it's, yeah, exactly. So it can get stuck there, but that's not, yeah, but again, that's not really the minimum, right? If it goes right or left, it will actually get to the minimum. And this, yeah, exactly. And the suggestion of actually calculating the second derivative, that's exactly how you know that you can go if it is at like a definite positive or if it is a definite negative.
Yeah, just adding a point here. If so, if just assume that the saddle some ant is there. Oh, it is like some saddle of some horse. Just assume, just for assumption I'm telling. If the ant want to move front or back, it will be moving upward. It's like going uphill. While moving uphill or in either side, we can find the rate of change. If the same, what happens if it moves in the left or right? Then it is taking down hills. So there also we have some rate of change. What I mean left and what I mean right is exactly we will be taking the straight line of action. If in case if it moves towards somewhere front left side, it will be moving a little bit up and little bit down. So that's where the gradient and the partial derivative comes into picture.
So just to clarify, second derivative just tells you whether it's maxima or minima, right? It doesn't tell you whether it's global minima or global.
I'm sorry, please come again, Rahil.
If you take the second derivative, you will only know whether it is a maxima or a minima, right? With
Yes.
taking the second derivative, you cannot say whether it is a global point. You can't say if it's global minima or local minima.
That's correct. Yes, you cannot.
I'm unsure
Yes.
about that. I'm
Yes.
sorry for this.
Okay.
I think the second derivative only confirms if it's like which way it's inflecting, whether it's a maximum or a minimum.
Right.
Yep.
So for example, if you're in 2 dimensions and one dimension, the second derivative tells you that you're at a maximum, and the other dimension, it tells you you're at a minimum, then that's one way to figure out is that you're really at a saddle point. Because you see in that 3-dimensional drawing that we just saw, if you go across from left to right, it reaches a minimum, but if you go forward to back, front to back, you can see it reaches a maximum. So if y was the direction left to right, if x was the direction left to right, then the partial derivative with respect to x would say that it's reaching a minimum. The partial derivative, and if y is the direction front to back, then the partial derivative with respect to y would tell you that you're reaching a maximum, right?
So in this scenario, what point would you be wanting to choose? The point where the red dot is currently would kind of be the best of 2 worlds?
It's kind of like a local minimum right there, but if you kept rolling down, you would have a better chance of reaching a global minimum, right? So
like what you said, that would be in the forward backward direction. So that's in the y you would be sacrificing for x, right?
Yeah, but right. I mean, in other words, the decision to make is, hey, I'm at a local saddle point, so I should go in the direction where the slope is, where the hill is going downhill. So you would choose the y direction, as I defined it, the front to back direction, to continue on, taking a step in that direction.
Okay.
Yeah, thanks all for adding these discussions. So,
and maybe if I can also add, so talking about, and
yes,
and you guys can chime in on this. So really, if we think about it, there isn't really a guaranteed way to say, hey, we are at the global minimum. I just wanna make that clear. You see, but that's why the initialization is very important, you know? That's why usually we do like a random initialization of the parameters.
Yeah, initialization also matters. One thing that while initializing, we should initialize in the way that all the values should not be 0. If all the values are 0, what will happen is we will be sticking only with 0. While we make some multiplications, we will be sticking with zeros. We don't, our model does not learn anything. So that's the one cap that we have. While initializing, it should not be random. So while initializing is random, though it is random, it should not be zeros. And in deep learning techniques, we can find those initialization steps that we I guess it will be, we will be going forward, we will be learning those steps. Yeah, so yeah, can we see polynomial regression now, or hello?
Yeah, we can hear you.
Hello.
Yeah, we can hear you.
Yeah. So far we have seen gradient descent. So in gradient descent, we are finding it's a way to find optimal parameters for optimal parameter theta. It's a way to find the optimal parameter theta. Okay, then we will see polynomial regression. So here we will, so far we have played only with the variable feature x1 and the feature x2. What if we can do, the thing is, since this is a regression, if our when we look through our data, if we find some straight line in some form, whether it is a direct as is x1, then when we apply some function over the x1, for example log of x1, then we may get some direct straight line. If something occurs, then we can just take them and plug it in our model. So that's what in polynomial regression. So here, that's one thing, that is finding the linear features. And here they have specified that in this example, degree is 2. So then the degree is 2, what it means is then x1, then x1 square, those kind of things will be taken, and that will be computed. And in the intercept, here we can find that one corresponds to the x square, and another parameter corresponds to x1. So instead of learning in the naive way, only one parameter for x1 alone, we are just adding some synthetically adding, so that whether it decreases, whether my cost function is reduced or not. If it reduces, if the accuracy, the quality is improved, then I will go with this one. There is no thumb rule that we have to do this, like that. Everything depends on, if it is better than yesterday, do this. It's like that. So when we take the polynomial degrees as 3, then we can find a square, a cube, these kind of combinations, we will get it. Yeah, so that's what is the polynomial regression. Usually when you do polynomial regression, it is like we are adding some extra information which may or may not be redundant sometimes. So accordingly, our quality of the results will improve. Yeah. Then the next step is learning curves.
So before we move on to learning curves, let's just make sure that everyone understands this idea of that polynomial regression. Even though it doesn't look like it, it is the same as linear regression. I mean, it can be cast in the same terms. So at first, when you look at something and it says, you know, ax squared plus bx cubed, you know, plus cx to the fourth, you say, oh, that's highly nonlinear. That's not a linear model. But if you redefine variables, if you redefine your variables x, and if you define x squared to be a new variable u, and you define x3 to be a new variable v, then you can write down a model that's y equals ax plus bu plus cv, and then you have a model that's linear in the variables x, v, and u. So even though intrinsically the model is really nonlinear, but you can write it down in a linear form, and therefore you can deal with it with the normal equations or SVD. So this is an interesting point. Also, if you have a model like, if you're adding a sinusoid, like if you say 7x plus 25 sine x, that can also be, that's highly nonlinear also, but you can regard it as a linear model if you define sine x as a new variable u. And then you can say 7x plus 25, y equals 7x plus 25u. Y is a function of x and u, and it's a linear function. If that makes any sense, I hope.
Yes, yeah. It's like we are synthetically adding some new features based on some from the current existing features. We are adding new features with some manipulations on the existing features. We are adding new features. Here in this scenario, we can say x1 is the only feature available. Then I'm newly adding the new feature x1 square, and then the model will be linear with these parameters. So it is like that. So yeah, as Joseph said, we can use, instead of x1 square, we can make the sin x or log x, so whatever it is. So whichever the linear trend we find, we may add, since we will perform linear regression. Yeah. And if you want to capture the non-linear information, linear regression is not good for. There are some more, some other best things are available. Why this is because why this polynomial regression comes, because it's all evolutionary. Now we are starting with the linear regression. So it does not perform for until some extent it will perform. After that it does not perform. So to overcome that, how can we overcome? Like that, after some research, we get this polynomial regression. So it's all evolutionary. Yeah. The next stuff is yeah, I think we can see this learning course the next time. Yeah, so I need to, yeah. Hi team. Hello.
Yeah, we can hear you.
Yeah. Sorry. I think we can continue the learning course in the next time, in the next meet. Yeah.
Sounds good. Yeah.
Yeah. Since so it's morning for me and it's evening for us. Evening for so I have to carry out the other tasks. So sorry for that.
Thank you, Rajesh Kumar. That was a great lesson. You took us through a good portion of chapter 4.
Yeah.
So, any questions from anyone? Or anybody want to discuss anything? I mean, yeah. I mean, yes, that was clear. But maybe if anybody has any questions, we can just talk about it. If not, that's fine. Okay.
Yeah. Please please reread the chapters and reiterate. Definitely, we will have some questions. Please keep posting on the Slack. Then we will get it forward. We will get it solved.